probably people in the room are at very different levels. And my initial idea was it's possible to write a web crawler in just a handful of Mathematica commands. So I had the handful, but every time I spent a couple of days working on this, every time I tried to explain it in 20 minutes for people who don't know anything about programming, I got stuck about halfway through. So what I'm going to do is instead I'm going to take you most of the way toward the web crawler. I'll show it to you at the end of the talk, and then if you're interested in this example or in other similar examples, I'd be happy to go over it with you offline. So let me just say a little bit about what I'm thinking. There's probably three kinds of people in the room. There's the people who don't program at all. So I hope what you take home from this is that you can actually accomplish interesting and beautiful things with just one or two statements. Okay, so that's, if you don't program at all, this might give you some ideas for why you might want to learn a little bit about programming. If you're already a programmer but you don't know what functional programming is, that's kind of a second class of people. Well, this might give you the sense that there are different ways to program, different kinds of idioms or different ways of thinking about how computation works, and that it's fun and interesting to explore taking on these different kinds of mindsets. And the third group of people I imagine in this room is that there's some people who already know what functional programming is and maybe do it and possibly do it way better than I do. And for those people, maybe this will just give you some sense of what kinds of fun things you can do in Mathematica. So think of this like a mechanical bull. It starts off slow and then it goes faster, and at some point maybe you get flung off or maybe not. Okay, so what functional programming is not is what's called imperative or procedural programming. So if you've learned a little bit about computers and maybe your first programming was in BASIC or some language like that, you learned how to set a variable equal to a value. So you might say variable equals 1, and when we do this in Mathematica, it just returns a 1. Or we can create what's called a list, a collection of elements, by putting them in curly braces. So here's a list of 4 things, A, B, C, D. In most languages, you can refer to a piece of the list by specifying what's called an index. So the second element of the example list is B. And the classic statement in an imperative kind of style would be something like a for loop. So what the for loop says is it says we're going to set a variable equal to 1. And as long as that variable is less than 4, we're going to keep adding 1 to it, and we're going to do something each time through the loop. So this is a kind of a classic imperative or procedural statement. You tell the computer what you want it to do, and part of the way that you manage that process of what you want it to do is by storing a temporary value in this variable, and that value keeps changing, and you look at the value. So if we run the for loop, just like any programming language that you're probably familiar with, it prints out A, B, C. And you might say, well, why didn't it print out the whole list? Well, because we said as long as I is less than 4, and this is a kind of a classic error. When you first start to program, for loops are frustrating because you're always getting things off by 1. That's not functional programming. In an imperative program, we change some part of the computer, and that stays changed in some sense. That's called state. So our variable I that we use to control the for loop still has the value that we last left it with, and that value was 4, even though it only printed out 3 things. If you try to think of your programs in terms of, if you have a whole bunch of programs and you're running them and they're changing state in the computer and you lose track of what's happening with the state, you can get weird kinds of side effects. So for example, if we go on and use the value I later on and we forget to put a 0 in it, the fact that it has a 4 in it might be a problem. This kind of thing, these kind of side effects are one of the reasons why people decided to explore other ways of programming. It turns out, in a kind of a mathematical sense, it turns out to be kind of messy to keep track of what variables are doing. And if we can get rid of variables more or less altogether, we can do interesting things with programming. So this idea of functional programming, we try to get rid of state, of mutation, of changing things in the computer, and instead we do computations in mathematical terms as functions. We have a representation, we do a mathematical function on it, and we get another representation as a result. So let me show you some examples of how this might work. The kind of classic functional idiom to do what we usually do with for loops in an imperative language is something called map. And what map does is it takes something like a list, and it takes something like a function, and it applies that function to each element of the list, and it returns you a new list where the function has been applied. So example list, remember we just set the value to A, B, C, D. If we go map and we map the print function across that list, we're going to get A, B, C, D again, as those are the side effects. Each time it evaluates print on the element, it prints it to the screen. It's also going to return a value. And in each case, cause a side effect, to put something on the screen, the value that it returns is null. So when we map print across our list, we get a list of 4 nulls, as well as having the side effect that we wanted to happen. One of the things that's important in functional programming is that a function itself is what's called a first-class object. You can do things with a function. You can pass it as an argument into other functions, and it behaves just like variables or parameters or arguments do. Let me show you another kind of functional idiom. Here's another example of map. We have our example list. It's still set. There's a command in Mathematica called framed, which just draws a box around something. So if we go framed on example list, it's just going to put a box around our A, B, C, D. What happens if we map framed across example list? What happens if we map frames across example list?
It's going to put a box around map D, B, C, D.
It's going to put boxes around each of them, right? Here's another command, another functional command. There's something called nest. If we say nest framed across example list, and we do that 4 times, it applies the function to applying the function to applying the function to whatever we apply it to. So we end up with a nesting of 4 boxes. And there's a command called nest list, which will give us the list where it does this, where it gives us the entire list of functions that we get out as a result. So when you start to think about programming in functional terms, instead of in terms of things like for loops or while loops or if then else statements, you end up thinking in terms of patterns, where if you know what one representation is, you apply that pattern to the representation, you end up with more patterns. I will not show you any more examples of that just yet. I'm going to keep going. One of the things, I said functions are first-class objects in most functional programming in general. What that means is that if you define a function, you want to define a function if you're going to reuse that little bit of functionality in some sense. So for example, suppose we think it's really important to add 2 to things. Well, in Mathematica, we can define a function like I just did there. And if we map +2 across this list, 1, 2, 3, what we end up with are each of those elements with 2 added to it. So we end up with 3, 4, and 5. This is great if +2 is an important thing in your world, and you're going to want to go back to it over and over. But what happens if you just want to do it once? Well, in Mathematica, in other languages like Lisp or Scheme or Haskell or something like that, you can define what's called an anonymous function. And what an anonymous function is it captures the essence of a function in a form that's going to vanish as soon as you're done using it. So in Mathematica, there's a syntax that involves what are called slots. These are the little hash marks. And if you use this slot syntax, you can define what is basically a function without giving it a name. So we can get the +2 functionality by mapping this anonymous function over a list. But as soon as we're done executing the map and the anonymous function of the list, the anonymous function disappears. So we don't create a side effect of building a whole bunch of functions that we're only going to use once or we're only going to use in limited context. Okay, let's do some fun things with texts. That's probably familiar and familiar to everyone. In Mathematica, you have access to all kinds of curated data. So there's the US Declaration of Independence. It's just sitting in there for us to do fun things with. The short command shows us a little piece of it. And what we can do is, this is what's called a string, ordered collection of characters. We can turn it into a list with a command called string split. And what I'm doing here is I'm getting rid of all of the punctuation marks and stuff like that, so I just have the words. And so basically we now have a list of words that we can do some fun things with. Okay, one of the things you might want to do is take pieces of lists. So there's a command called first, which just gives you the first element. There's a command called last, which gives you the last element in a list. And there's a command called rest, which gives you what's left of the list after you take the first part away. And if you're familiar with a language like Lisp, this is the famous car encoder, which you use to take lists apart, do something recursive with them, and assemble everything back together. In Mathematica, there's a function called memberQ, which lets us test for membership in a list. And we're just using memberQ to show that the word human occurs in our short sample and the word alien does not. Okay, we can use map to process every element in this list too. uppercase, we can map it across your list. You can convert things to lowercase by mapping it across the list. You can measure the length of each of your characters by mapping something across a list. So this idiom of mapping something across a list makes it very easy to manipulate things like text as long as you represent them as lists. Computing word frequency, something you might want to do, becomes relatively easy. We can sort our list into we can sort the Declaration of Independence into all of the word tokens that appear. There's a command called tally, which lets us compute the frequency of our words if we want. We can sort that by the frequency, and what I'm using, this is another case where I'm using an anonymous function down there to tell sort what kind of behavior I would like it to have. So it's one of the parameters that sort takes is a function named or anonymous that you can do fun things with. And you can ask me about that a little later. I didn't explain it very well. Basically, this shows us that the most common word in this text is of, occurs 79 times. The determiner occurs 77 times, and so on. Some words, like abolish, only occur once in our text. We can find the frequency of any particular word with something that selects elements out of a list according to a pattern. N-grams, okay, we've probably been following the whole Google N-gram thing. Maybe it seems kind of mysterious how you end up with a collection of N-grams. In a relatively high-level language, getting N-grams is as simple as one command. Here we're using a mathematical command called partition, which simply gives us a kind of a sliding window. In this case, we're doing bigrams of pairs of words when in the course and so on. If we want, we can sort our bigrams and count them. And so we can see that the two-word phrase he has is the most frequent one in the Declaration of Independence. So we can do useful things with pieces of text quite easily in this scheme. Something like a concordance. Again, some people spend lifetimes generating concordances. You used to want to buy software to do a concordance. There's a bunch of $150 Windows programs that will create concordances for you. Again, a concordance in this idiom, concordance is one statement, basically. Here we're looking to use the mathematics pattern language to specify that we want to see all of the 7 grams that the word powers appears in the center of, and kind of voila, instant concordance. Pulling out stop words, again, I'm going to use some of the curated data. In this case, what we do is we're going to pull out the stop words, but we want to keep the text in the order that it occurs in. The reason that we want to do that is we're going to look at kind of frequent bigrams in the sense of we have when in the course of human events. We're interested in things like human events. We're not so interested in things like in the, because those are stop words. So if we pull out all the stop words and we keep our sample in the right order, we end up with course, human events, and so on. And what we can do then quite easily, we can find which bigrams contain the most frequent words. And now I'm really not explaining things. I'm just going through for a bit of gee-whizzery. We pull up these frequent bigrams, find out which ones show up the most often. And then it becomes quite simple. Again, now this is just if you can follow this, that's great. If you can't follow this, it's one line of stuff, so you don't have that much to learn. We end up with a kind of a map of what bigrams are frequent as a directed graph. So reasoning from a text to a directed graph becomes quite easy because, again, we're thinking in terms of mapping functions over lists. Okay, one more thing. Mathematica has a command called import, which can be used to scrape web pages. So here we can just go through it and scrape, say, all of the hyperlinks off of, I just use my blog as an example because I know it doesn't have very many links on it right now. And here's the one that I had hoped to explain to you in 20 minutes. This is a full-on working web crawler. So let me run that. It's going to take, a second to run. So let me just run it. So let me just explain quickly what this does. What it does is it starts with a particular URL, in this case my blog. It pulls all of the hyperlinks off of that URL. And then it uses that command that I showed you a few minutes ago, nest list, which builds up lists of stuff, to iterate the scraping process. And it's pulling back the hyperlinks, what they point to, more hyperlinks, and so on. We take it to a depth of 2 jumps because we don't want to spend all day doing this. But basically, if everything works correctly, which it should, but it should also take about 40 or 50 seconds. If everything works correctly, what we'll end up with is we'll end up with a map of every link from this web page to this web page, this web page, this web page, and so on. And we have basically the sort of gist of my blog is in the center, and some of the other sites that it links to are around the edges, and each one of those links and so on. We end up with a map representation of a neighborhood in hyperspace that we can then, in hyperlink space, that we can then do other things with. So that was the example that I kind of wanted to show you, just in the sense of what kinds of things you can do if you're working in a high level and kind of functional way. There's one other thing about working with programs as functions, which is kind of fun, and that is if you're the kind of person who likes beautiful things, symmetric things, things that make sense in kind of an abstract way. If you perhaps know something about abstract algebra and that's something that you're interested in, one of the really cool things about reasoning with programs that are functions is that you can then do algebra on your programs. So by getting rid of variables and side effects, what you end up with is a system that allows you to use the tools of abstract algebra to generate new programs, to create proofs, to create more efficient algorithms for doing the same kinds of things and so on. So it's worth, if it's the kind of thing that you find beautiful and fun, it's worth exploring a little bit. You can learn more about Mathematica, which is a commercial and somewhat expensive system to play with. It will cost you about $400 per license. You can play with it, and about $1,200 per license to do everything you want with it. If you just want to explore functional programming but don't want to get into Mathematica, there's a pure functional programming language called Haskell, which has a great online presence and a lot of tools. Scheme and Lisp, of course, are kind of classically used in computer science programs to teach functional as well as other styles of reasoning. And then there are languages like Perl, Python, and R have functional constructs. So you can do a bit of this kind of work in those languages. You can start to think in terms of commands like